Okay, let's officially get started here. So we're going to start out with database normalization, which is assignment number 5. And there's a little PowerPoint lecture I'm going to do on this so that you can understand what normalization means. We started the course out doing entity relationship diagramming, and in that we made third normal form databases. And I talked about normal forms a little bit back then, but I really haven't gotten into the theory or what it is we're doing. If you're using an entity relational model and practicing good entity relationship diagramming for your database designs, you are already putting stuff into third normal form. What you're looking at in the assignment is a database that is not in third normal form, and we're going to stick it in third normal form. Because probably in a few minutes I'm going to go through the normal forms, tell you what that means. But if a database is in third normal form, it's pretty average. It's like a C. If you were going to put grades on a database, it's like a B, C range. It's not really an A. I'd say third or fourth. Third plus B and C, or B and F. And I'll go through that in a few more minutes. There's other characteristics we can add to it. The normal forms are telling us the quality, the grade that we're sticking on the database. Why do we care about grades? Because a B quality is better than a D or an F quality. I mean, you think about it from a student perspective and grades. And why do we grade it? Because an A quality or a B quality database is easier to search, and it's easier to find data in, and it's usable. And a D or an F, the data may not actually be findable, it may not be collectible. So I'll go through the assignment when I'm done going through the lecture, because the assignment itself isn't going to make very much sense to you. But what we're doing in the assignment, so you can think about it in the back of your mind, and we'll do this together. We're going to analyze the table design given below. Here's the table. We have a customer order table, just one table. We're going to break it out into different tables. We can actually even build it in MySQL if we want to. And then when we build it out, we're going to document a few things about the table. And so we're going to normalize the table, put it in third normal form. We're going to create these things called functional dependency descriptions that I'm going to talk about, show you how to do it. And then we're going to create a simple table description for the final table list. So we're going to look at, in this exercise, also how to document database, dependencies, and document foreign and primary keys and stuff like that as well. So this is called a functional dependency description, where it says column A leads to column B, comma, column C, comma, column D. So we have this functional dependency, and you don't know what a functional dependency is yet, so we're going to get there. Or in this particular case, we have these two columns, column A and column D, functionally dependent upon column E and column F. So that's another way of doing it. And then the table description down here, where it says table A, and it has column A, comma, column B, column C, and column A is underlined. You may be familiar with this notation so far because we've done this in some of the previous assignments when I've said, give me a list of columns or give me a list of tables and table information. And then the part underneath it with the foreign key is going to give us our sort of the syntax for how we're going to do our references from our foreign to our primary. So this is table D here. So we'll go through this when we, so what we're going to do is take this list down here, separate it out into different tables following a methodology I'm going to show you in a few minutes, and then document it like this so we can tell which foreign keys go to which primary keys, et cetera, so forth. So that's the process that we're going to go through, and that would be what we're going to do for assignment number 5. So before we can get there, we got to kind of go through the steps of normalization. And that one, as I pointed out, is in the normalization lecture. That is, let's see. It is in the Canvas class. Oops. Okay, it's not going to come up with this one, but I just showed it a few minutes. It's pinned. I pinned it. I called it normalization.ppt. So that's the one that's going to be the lecture we're going to go over right now. So let's see. It's also, I believe, lecture 8. Uh-oh, what happened to your computer? I heard a weird noise. Huh. Okay. So let's see. What we're going to look at is the normal forms. Is it working? Is it actually working? I don't know. Let's see. Let me hold on for a second. Okie dokie, let's get started again. All right, so this is the database normalization, and you fortunately got that right from the beginning, so you're in good shape here. We're going to look at normalization, the role it plays in database processes and database design, what it means to be in first normal, second normal, and third normal form. We'll also look at BCNF formats, and fourth normal form, which is interesting because most people go, well, third normal form is like the de facto standard, and it doesn't really matter. There's no password, just press return. There you go. So, bottom line, fourth is not always better than third. Third's not always better than second, but third is pretty normal. I mean, it's pretty normal length. And it's characterized by certain features of the database design. It's not necessarily a grade, as I was saying before, but it's very close to the concept if you were to compare it with something else. So normalization normally happens through entity relationship modeling. As I mentioned before, the ERD diagram gives us third normal form. So it's just really what we're looking at. So the process is for evaluating and converting or correcting table formats. And it minimizes data redundancy, hopefully. Gives us better data consistency and removes any data anomalies or errors or inconsistencies in the data, which is why we're paying attention to this. And it works through a couple of stages. Now, we don't have to go through all of the stages. Sometimes you'll get a second normal form database and you can convert it into third. Sometimes you can go from a third to a second. You don't always get first normal form. So it might, especially if someone's taken a database class, the DBA who's putting the database together, and they're already familiar with database design, and then they start putting it together. Sometimes you get like a nice second normal form out of it. You might even get a third normal form, depending on how many darts you throw and how the darts stick to the board. But what we're really doing is looking at the characteristics. So second normal form is technically better than first normal form, and third normal form is technically better than second normal form. But there are cases, and I'll wait till the end of the lecture to go over this. There's some cases where we want to go down in the normal form on purpose because it just makes it easier to search a table or eliminates a join on a table or something. So most businesses and most business designs use third normal form as the highest they need to go in the normalization process, and the highest level of normalization is not always the most desirable. So keep that in the back of your mind in terms of why we're doing this. So here's an example that we're going to go through, and the example is a company that manages building projects. So we have building projects, and this is the same example we used actually in another lecture a couple weeks ago. It charges its clients by billing hours spent on contracts. And there's an hourly billing rate that depends on the employee's position. And periodically the reports are generated that contain information that's displayed here. So a lot of people do this actually. A lot of small business owners, they come up with these reports. And then they take the reports and they turn it into the database. Or they use Excel. Actually, there's a lot of companies that do this as well. Like small companies will use Microsoft Excel as a database. It's not a database program. But they don't understand the differences between. So they think, kind of like a database. So they take the sample report and they use that as their data. So it's not first normal form either. It's just garbage. It's a report. So we start out with no database, essentially. And what we've got here is a subtotal. This is a nice little report. Could be done in Excel. Could be done in any reporting program. Nothing wrong with the report. But generally what ends up happening, and this is a screenshot from Microsoft Access, it's the report placed inside of our, Excel. You can go into Microsoft Access and import an Excel spreadsheet, and it looks something like this. It's just rows and columns now, instead of this look that you get more of the Excel look with. This is the database look from Microsoft Access. We can actually get this in MySQL as well if we print out like just the data in the table. But we have some problems with this. There's some holes, and we have some missing information, and then we have some groups that are created because it came from the report format. Yeah?
Why we have like static signs in front of a couple of employees?
We have a what?
Like a static sign. Why do we have those?
Static? Oh, asterisk? I don't know. It's because it was in the report here. There's an asterisk in
Only
here.
one employee need.
It's basically this data. Somebody actually did this. Just stuck it inside of a table. It's the same data that's in the previous. Why there's an asterisk? Oh, it says indicates project leader. Yeah, so it doesn't make sense for the table, actually.
So can we import the Excel
You
to
can.
database?
Yeah, that's what this example is actually doing.
So
I don't necessarily recommend it because then you have to go through all the normal forms to clean it up. But you can, a lot of people do this though, especially if you're coming and you're just starting a business or something and you come in and they say, oh, we're going to make a database, right? And all they have are reports and things. So you could go from Excel, actually you can import Excel data inside of MySQL as well as Microsoft Access. A lot of people use Microsoft Access because they have it with, it used to come with Microsoft Office. I believe it probably still does. And I wouldn't call it a full feature database, but it works as a database. So a lot of people use it with Excel and they take the Excel spreadsheet in this particular case and then they import it into Access and they go, oh, I have a database. But it's not even first normal form yet. So, but it does provide a nice example to get us into first normal form.
This can go to like MySQL.
Yeah, you can do the same thing with MySQL. Yeah. Doesn't really matter what database you're using. The normal forms are pretty much the same as well in terms of characteristics. So this is good actually that we're taking some time to look at this report format. Not the best for a database. The structure in the data set in figure 5.1, and this was 5.1 here. This is the sample report layout. And put inside of a table. Handles the data well, but only for reporting purposes. It doesn't handle it well for database in terms of what we're trying to accomplish with a database. The table structure appears to work. The report is generated with ease, but unfortunately the report may yield different results depending upon what data anomalies have occurred. As an example, how this is ordered, what order we're putting it in. It might give us different results. Also, how did the data get imported in? Do the columns make sense? Do we have the proper calculations? Because the other thing they're not telling you is in here there was some subtotal calculations, probably a formula in there. I guarantee you probably don't have any formulas in here. You just have the raw data from the output that's put in here. So the formulas Excel formulas don't work in Microsoft Access, nor would they work in the same format in a MySQL database. So let's see. We're going to convert now to first normal form so we can see what first normal form looks like. So there's some repeating groups. And the repeating groups we have are here, where we have project number 15, project number 18, and this is a group. We have repeating groups because we have 4 groups. So this is what they're calling repeating groups. So it's derived when it's named from the fact that the group of multiple related entries can exist with any single key entry occurrence. It's easier just to look at it this way. Single key occurrence, multiple entries for one. So these are all really project 15. So relational database tables cannot have any repeating groups in it. So to get it into first normal form, we're going to get rid of the repeating groups. So normalization on the table will reduce the data redundancies. And then we have the normalization that will occur in 3 different steps. So the first step, eliminate the repeating groups. So there's another trick you can see in a few minutes with this. Take all the spaces and put something in the spaces. So it introduces data redundancy, and I'll show you why in a few minutes, but it eliminates the data redundancy from the repeating groups. So you present the data in a tabular format where each cell has a single value and there's no repeating groups and no empty cells. And then you eliminate the repeating groups by eliminating the nulls, or the empties, making sure that each repeating group attribute contains the appropriate value. And here we go again. So this is first normal form. So if you're looking at this, you see that 15 is repeated. It's called controlled redundancy. So it's kind of ironic. We put redundancy in to get rid of repeating groups. We change one redundancy to another. So if I were to compare this one with this one This is where I say that the trick is really we're getting rid of the nulls or the empties. So it says project number 15 with project name evergreen. And then we're going to fill this in with 15 evergreen, 15 evergreen, 15 evergreen. So it says here 15 evergreen all the way down. So we just added a bunch of stuff in there. We made it a little bit redundant, but it's called controlled redundancy because it's a control mechanism to remove the repeating groups. So now we have no repeating groups. We're actually in first normal form. So most databases that you put together starting with a database is naturally going to be in first normal, unless you import data like we did here with this Excel file. So usually you're going to get at least in first normal form if you're using database software. May not necessarily be if you're not using database software and you're just importing an Excel spreadsheet in for some reason. Step 2. Now we're going to identify primary keys. So we've introduced a bunch of redundancy. Now we can pull some of the redundancy out. As an example, do we really need to know project name, project number, project name, project number? Or is the project name going to give us the project number, or vice versa? Okay, so the primary key must uniquely identify the attribute value. And the new key must be composed if no key exists. And then we're going to identify the dependencies on the keys. So we're kind of going backwards. So if you started out doing an entity relationship diagram, the first thing you're looking at are the keys when you start looking at the relationships and the entities and putting them together. But if you didn't do that, this is the backward process to go look at the keys. So dependencies can be depicted with the help of a dependency diagram, which is the entity relationship diagram, which is why a lot of people use that diagramming approach. And the dependency diagram, it depicts all the dependencies found within a given table structure. And it's helpful for a bird's eye view, kind of gives you the bigger picture of all of the relationships among the table attributes. And then it makes use of much less likely than important dependencies will be overlooked. So this is a dependency diagram, slightly different form because we're still working with just one table. If we think about it, these little boxes are entities. And this is the diagram for the single table database that we're still looking at because we're only in first normal form right now. So we take the first normal form database and we look at the dependency and the potential keys. And then we start looking at partial and transitive dependencies. So I'm going to give you some more vocabulary here because we don't want partial and we don't want transitive. We're going to eventually get rid of all these dependencies. But we have to identify them in order to figure out which ones we want to remove or which ones should stay. So here's a partial dependency. The project number and the project name. So it's a project name, and then we have an employee number who's working on a project number. But the name could possibly change. So going back to this previous example here, we're allowed to put anything we want in this column here. So we could have project number 15, who is evergreen. Well, we can change the name to Amber Wave or something. We can change the name if we want. They just happen to all be the same name. But it is dependent. So if we look at this and we say, well, which project is employee number 103 working on? Well, it could be the evergreen project or it could be 15. We have two pieces of data that are going to be used to identify that. So employee number could be used for the project name. It also, project number. Project number could be used for project name. They're partial because they're not a complete one-to-one match. We've got two things instead of one thing, and these two things are partially dependent on each other. It's evergreen, the name is partially dependent on the number 15, the number of the project. So we want to get rid of that ambiguity, and this is really just more than an ambiguity than anything else. And then we have partial dependencies here with the employee number, who might have an employee name, a job class, a charge per hours, number of hours worked. And all that stuff might be on the project number, project name. They might have a employee name working on the project, and job class working on the same project. And then we have this transitive dependency. So the partial dependencies are when the complete picture can be read read in multiple different ways, and you can get the data derived in different ways. It makes it partial, which is weird. The naming is kind of weird to me. The transitive dependency is even weirder. It means one determines the other, and the other doesn't necessarily determine the other. Like A gives you B, but B doesn't always give you A. Then it's transitive, which means it can go away, and A can give you a different B. As an example, the job class. It could be, let's look at the job class here, an electrical engineer, a database designer, but the hours worked here, the charge per hour, could be different. So if I said, how much does a database designer make? And here it looks like 105. Let's see if we got a systems database designer. Here's 105. Application design, database designer. See, we got programmer. Looks like they're all making the same amount. $84 here. I don't know if these are realistic or not. Electrical engineer. In any case, one determines the other, but this one may not determine this one. Because the charge, you can have two programmers as an example with two different prices. They just happen to be the same because they came from a spreadsheet like this. But you could put a price in for what a programmer makes per hour that could be different than the job class. So by default, we'll see this happening in a few minutes here. It's a transitive. They call it a transitive dependency one is supposed to determine the other, but the other doesn't determine the first one. Doesn't determine it's like it only works one way, but it's supposed to work both ways. So for example, if I made $105 an hour, I'm supposed to be a database manager or something. Or maybe that's database managers that some of them make 105, some of them make something else. So first normal form, the tabular format is in first normal form when all the keys are defined and there are no groups. So we got rid of the repeating groups. And all the attributes of the dependents are on a primary key. And the table has a primary key. And all relation tables satisfy a first normal form requirement, which means all of the tables in the entire list of tables look like this. So and first normal form really is just no repeating groups. So, and then the dependencies might be based on they might have some partial dependencies, maybe based on only part of the primary key. And sometimes used for performance reasons, but just should be used with caution. You don't necessarily want to use a first normal form database, still subject to redundancies. So now we're going to convert it into second normal form. Relational databases can be improved with two steps. First step, identify all the key components. So write key components on separate lines, and you're going to create more databases. You're going to create more tables. What we're going to do so first normal form is all in one table. No repeated groups, but the whole thing is one table. We go from first to second by breaking it out and keying it. So we move the data out into separate tables. So we're trying to work on those partial dependencies actually. So each key attribute is on a separate line, and then we write the original composite key on the last line. Each one of these components will become a key in a new table. And then the second step, we determine the attributes, what belongs in which table, essentially, that are dependent on the other attributes. And at this point, most of the data on anomalies might be removed. So that one table turned into three tables. Turned into three tables because we have a second normal form conversion. So in the assignment number 1, we started out with, or assignment number 5, I believe, or I can't remember the assignment number that we're going to do today. It's been one table. Actually, it's not even a table, it's just a list of data components. And we can put that into first normal form by just putting it into a table format. And then we put it into second form by pulling it out into separate tables and keying it properly. So, for example, we have, it may be a table called project, and it has the project number and the project name. And then we have a table called employees, and employees has got an employee number, employee name, job class, charge per hour. We still have this transitive relationship in here because we've only gotten rid of partial dependencies. So we basically took these here, separated them out into separate tables. And then we have the assignment table. This is really a relationship table. If we write this as a relationship diagram, we have employees that work on projects. This is the works on project on the works on table. And we know it's a separate table because it's many to many. Many employees work on many projects. So So the employee number, the project number, and then the assigned hours, how many hours they're working. So because you know entity relationship diagramming, that can possibly make some sense to you if you were to look at it in terms of an ERD configuration. But we're still not in third normal form. We're still only in second normal form because we still have this transitive relationship within this one table here. So if we're in second normal form, we're also in first normal form. So second implies first as well. And it includes no partial dependencies. We've gotten rid of those. And no attribute is dependent on only a portion of the primary key. So now we're going to convert it into third normal form. So the data anomalies are easily eliminated by completing 3 steps to get it into third normal form. The first step is for every one of the transitive dependencies. Now we're going to look at the transitive one. So we still have dependencies inside of the tables we spread it out with. We're going to write a determinant as a primary key in a new table. And then the determinant is going to be any, by definition, it's like a candidate key. Any attribute whose value determines another value within the row. Like the project number is going to give us the project name, or the project code type is going to give us the cost per hour. And then we're going to identify the attributes that belong with that determinant. So we're going to identify the attributes dependent on each one of the determinants identified in step 1. And then we're going to identify the dependency. And then the table, we're going to name the table to reflect its components. So we're in third normal form after we've removed the dependent attributes in the transitive relationships. So we're in first and second. We eliminated all of the pieces that were dependent upon each other or partially dependent upon each other. We can draw the dependency diagram, and this will actually turn into an entity relationship diagram. So we've checked the new tables, modified the tables in step 3, make sure that all of the determinants that don't contain inappropriate dependencies. And then we get this. It's not drawn in an entity relationship diagram, but it very well could be. Because what we've done now is in the second stage, if you relate this to working and determining an entity relationship diagram backwards is what we're doing. We're going back the opposite direction. So instead of starting with the description of the database, identifying entities and their relationships and drawing the lines and everything in between, we've started with the data pretty much. And now we're going from the data backwards. So this over here, this name over here, is really an attribute. It's a multi-valued attribute. So it's the same diagram we saw before where we have employees who work on projects. And then we have employees that have an attribute, job class. And the job class, like a database manager, programmer, has a charge per hour. So everybody in our system makes the same charge. Like if you're manager level 1, 2, 3, you're at a certain pay grade. So that's where your charge per hour comes into place for your pay grade. This is a third normal form database. And you're like, well, if we had just started with entity relationship diagramming, we would have gotten this a lot faster. Problem is, there's 2 approaches. You can work through from the data to create this, or you can start and create this and then populate the tables with the data. We've been going the opposite direction. We've been working with the data from an ERD description and then going from entities to relationships and figuring out, well, which ones of these relationships are multi-value? That becomes a separate table. And then which one of these entities, they become separate tables. And then the multi-valued attributes become separate tables. So it's kind of an interesting phenomenon the way it kind of goes both directions. So most likely when you get out into the real world, you're not going to be able to start fresh. Unless the company's brand new and they're just starting out. Instead you get data. And you got to go take the data and list out all the tables that they have, and then kind of go through and check for partial dependencies within the table. Usually what I find is too many tables. Like you got 2 employee tables, or you have an employee table for every one of your job classes. Did you have a question? I saw your hand going up. Yeah.
Table name assigned. There are 2 primary keys.
Over here you have 2 foreign keys. It's a relationship table. So this project, okay, if we started out like an entity relationship diagram, I would say that employees work on projects. The employee and the project are two entities, and the works on is this assign table. And it's assigned, it's in between. So if we had like a entity, a diamond for the relationship, and a project, the diamond in the, this is the diamond in the middle for the relationship. And it's a many to many. And we're bringing it together by taking one key from here and one key from here to represent the relationship. And this is a primary key, and these are two foreign keys. That's actually a second normal. And then if you stick this in here, that's a second normal. It's a third normal when you pull out the multi-valued relationships and you take and you consider that we're going to get rid of the transitive relationship. Get rid of the transitive relationships, which I like to instead, I don't like the word transitive relationship, or transitive dependency. I'll just say it's really a multi-valued one. One's going to determine the other, kind of, sort of. Multiple values. So for example, job class programmer and the charge per hour. Now, if the programmer job, there was different types of programmers and they didn't all make the same thing, which is kind of unrealistic for the real world. A lot of people make different amounts on different jobs. So if that's the case, then you don't necessarily need to do it this way, because then you'd have to go programmer 1, programmer 2, programmer 3. If that were the case, you can get rid of this relationship completely. If the job class doesn't determine the charge per hour, you could just stick it back in here in the employee, and it could just be like charge per hour and title. So it doesn't necessarily need to be brought back. It just means if you can have multiple jobs. So this is what puts it into third normal form. And the question is, well, what about just a second normal form? It might be easier to search to see. If you're trying to figure out how much an employee makes, it might be easier to figure it out by a job class. And then in the job class table, you can just change it every year for inflation. But if you have it in the employee table, you got to update every single entry in the employee table versus just one place, and then everywhere the job class is mentioned, it's going to bring in the same number. So if you want consistency, and this is really just giving us consistency, the third normal form gives us better consistency. Otherwise, we could have the same job class with different same title with different pay, which we might actually want. And if that's the business rule, it might lend itself better to a second normal form format than a third normal form. Which is what I was trying to say before. Don't worry about, going from a third to a second. You don't want to be in a first. I mean, that's all in one table. So if you're in a first normal form database and you're searching it, that's a lot of data. It's all in one table. You break it out, get into at least second. You might not have all your partials and all your, well, maybe you don't have all your transitive dependencies determined to get yourself into third. But second might actually be okay at that point. So third normal form, you're in third normal form. If you're in second normal form, and it contains no transitive dependencies. You don't have any transitive dependencies in there. So you can improve the design, believe it or not, past third normal form as well. So the table structures are cleaned up by eliminating the troublesome initial partials and transitive dependencies. And normalization cannot by itself be relied upon for good database design, which is kind of like the why you have entity relationship diagramming as a concept. It puts you into third normal form automatically. So it's valuable because it helps eliminate data redundancies. So how can you improve the design? To go into fourth normal form, or to go into what we're going to look at next, BCNF. Because most people are like, well, that's pretty good. I would get that if I did an entity relationship diagram. That's good. So the following changes were made so far. We have primary and foreign key assignments. We have naming conventions that we might want to look at, like the assigns. So you can improve the design by clearly identifying the primary key and only putting one in there. So the other thing people do is they go employee number, and then employee social security number, and then employee ID number. And then they have all of these different pieces of information that they're going to stick in the same table to identify an employee. So you have basically multiple keys. And the problem is when you go search it, you don't know which key is used as the key. So there's confusion with that. The other thing that happens in that scenario is that you might not even know that the table is actually called employee table. It might be called table 1, table 2, table 3. It's kind of amazing when you go into some databases and you see table A, table B, table C. It's like, what? Or you go, oh no, that's the employee table. Well, the faculty table has the students in it too. Or the employee table has the more than just employees. It has like the president in there too, or something. Or I don't know. It just has people in there. So properly naming the table helps, because what ends up happening is people create the database one time, and then it's used for many years. And 10 years down the road, the people who actually created the database aren't even with the company anymore. And so you go in and look at this database, you're like, oh, employees. Does that mean faculty, student, teacher, everybody's in there? Like, okay. Or is this table just students? So it's kind of interesting, the naming conventions. Also, attributes, atomicity, and keeping attributes consistent. People have problems with that when they make everything text. So sometimes you look at the data type that's used for the field and it says ID. Sometimes the ID is a number, or sometimes it says programmer, like a text string or something. And then you have interesting cases in which you don't even know what these attributes are either. Or sometimes there's an attribute there, and then in other cases there's no attribute. Like if you make an attribute for an employee ID, which is actually kind of funny because people used to use visa numbers for student tracking, right? I mean, everyone's got a visa number, right? But what if you're an American and you don't have a visa? You're going to put social security number in there. And then for the longest time, people were like, okay, let's use social security number. And then like, okay, well, international students may not have a social security number. It's like, oh, because years ago you never required one. So then you have sometimes it's in there, sometimes it's not in there. So you just want to do a simple query. How many students do I have? Well, it depends on what you're searching on. You're going to take this number and add it with this number and add it with that number, because some of them have visa numbers and some of them have social security numbers and some of them have nothing at all. So it makes it hard to actually query the database. So you're doing third normal form to make it queryable. You might have extra attributes. Like you're in a student table and you have your name and you have your address. Or you might be missing an attribute. Most student tables will have a home address and then a school address. Because if you just put one address in there and then you change the address, you don't know, like, is this the dorm? Is this like the traveling address? Or is this like the home address? And then you have your transcript that gets printed out at the end and you've moved from the student address. Anyway, bottom line, the addresses are interesting. Or you only have one address. It just says address. No city, state, or zip. So then you have to think about it like, okay, do we want to know what state everybody's living in? Or what city people are in? So you'd be able to search on it if it was broken out. Maybe adding relationships as well might be an issue. Yeah. An attribute of a data would be one of the columns, like here. One of these columns in the table. These are the attributes. The column itself are attributes about the entity. An attribute is a column piece of data that describes the entity. So it's an attribute of an entity. This would be called an entity if we're going to look at dependencies and entity relationship diagrams. And inside are the attributes. Data about the data. Students have attributes. You have a name, first name, last name, social security number. Those are the attributes that would describe a student. Attributes describe the object or the entity. They are equivalent to the columns of the column name. For example, if I did address, like just the word address, I could put 123 Sesame Street in there, San Jose, California, 95, whatever. All that stuff. It would be like a string or something, a very long string. That would be one attribute. Versus 3 or 4 attributes: city, state, zip, street address. So what I was saying is, like, the form of the data could be significantly different for searching. If, for example, you want to know what state are the students in. If you had a separate attribute called state, along with one that was called city, and then another one that was called zip code, you broke out the attributes, you'd be able to see them more clearly. and then you'll be able to search on states or street addresses or zip codes. Yeah?
I'm so sorry for interruption.
Oh, yes.
11 o'clock.
What happens at 11?
We need you out here.
Okay.
If we could have you at lunch at 11.
Okay, perfect.
Fantastic.
Perfect.
Sorry for interruption.
Oh,
Thank you.
I think they needed me out there. You can go out there too at 11 probably. Yeah. I probably shouldn't have broken this, but I did. Let's see. Maybe I can go back from current slide. There we go. Okay. So there's a open house today. I believe there might be muffins or something at 11. So, or food. Fruit? Oh, you saw fruit? Oh, excellent. I thought I saw this thing of muffins. So, oh, there are muffins? I was eyeballing one of those muffins. The fruits I can have any day. The muffin. Anyway, we'll break it into another 15 minutes and make sure we're out there before the rest of them come out there. We'll be the first out. So, well, we have such a small group, so it's okay. And adding attributes, adding relationships. We could add a relationship to the table, and what we're trying to do is improve the design. And we could refine the primary keys and the foreign keys, maintain historical accuracy, keep records of everything. We also may be able to use derived attributes. So instead of arbitrarily giving somebody a number, we could have a sequence or something where each student who gets added in is a number incremented by another number. So it could be 1, 2, 3, 4, 5 or something, and then add some meaning to it of some nature. So here's the complete database design that we had. This is the tables for job, project, and employee. And it's just a review of what we ended with third normal form. Now we can improve a little bit with this. This is actually just two of the tables, the project table and the job table. And then we have the assigned table and the employee table. Now we have these things, these limitations on system assigned keys, which is why you want to use meaningful data. So as an example, if the IDs of the project IDs here as an assigned number, like it's like 1, 2, 3, 4, 5, or 101, 102, it doesn't make any sense sometimes. Like, if, for example, the reason why you'd want to use a social security number versus a number, if I just gave you a number and said you're number 100, 5 years from now, you're going to go, what was my number? I don't know. But if it's a piece of data that you're carrying around with you, like your visa number or your social security number, you're going to remember that number because you use it for multiple different things. So if someone said, hey, I went to this university, 10 years down the road, and I need to order a transcript. I said, they're going to ask you a piece of information about yourself. Well, what was your number? Like, I don't know. It was 100. I don't know, because you're not going to remember that. But they said, so usually they'll ask, well, what was your address? Where did you live at the time? Or what is your social security number? Or what was your visa number? Or something like that. And then that information can be used to look you up. So sometimes, and you don't think about databases as being something that someone's going to go to 20 years down the road. But that's a classic example of transcripts, actually. Because, further down the road, you might actually want a record, a birth certificate. I don't know, you might want something from a database that, so anyway, limitations on system assigned keys is they're meaningless. They don't have any, like the word, like the number 100 doesn't mean anything. So some limitations on that. The key may not prevent confusing entries as well. So the data entries in 5.2 are inappropriate because they have duplicate existing records, maybe. Yet there may also have been some violations or no violations in either the entity of the integrity or the referential integrity. And so this is what we have here. We could have two different job types or two different job names. So if I go back to this, here, this is a little bit easier to look at. I could have programmer with $10 an hour, and then programmer with $20 an hour, and programmer with $50 an hour. Unless I make this and enforce the referential integrity. So we actually did this with some of our databases. We went into third normal form, but we didn't at one point, well, we did eventually, but at one point we didn't link the primary with the foreign. So it's a good idea to actually, if you're going to put the referential integrity in there, to enforce it, which means primary keys have to match up with foreign keys, or foreign keys have to match up with primary keys. So here's an example of duplicate entries for the job table. If you have job code 511 and job code 512, and they're both programmers, and then they're both making $35.75. Well, you have two different job codes with the same job descriptions. So you can improve upon the design by making the job description field unique, maybe, or not allowing the same programmer job title or job description to be assigned to the same code, having different codes. So this is where the Boyce-Codd normal form, BCNF, comes into place. So you can be in third normal form but not in BCNF if you don't have referential integrity put into place. So every determinant in a table is a candidate key. So it has some characteristics as a primary key, but for some reason wasn't chosen as a primary key. Or you have multiple primary keys. And you didn't choose one piece of data. It's like having a social security number and a student number. If the table contains only one candidate key, the BCNF and third normal form are equivalent. BCNF can be violated only if the table contains more than one candidate key. So you pull out the extra candidate keys. And what I mean here is we have a job title called a programmer. That could be the job title and the job code. Both of them could be candidate keys. Because we could say, well, what's your job code? 511. Because here's the thing. If you change one of them and you're looking at a programmer, depends on which programmer you're talking about. Maybe this one's $55 an hour and this one's $35 an hour. This is not BCNF. It's their normal form, but it's not BCNF because you have multiple determinants. So if you just had one job code with a charge per hour or job description and then these are not the same, you'd have better consistency when you go to look at how much a programmer makes. So let's see. So every determinant in the table is a candidate key. If the table contains only one candidate key, and it's BCNF and third normal form are equivalent. So they're not equivalent if you have more than one candidate key. Most designers consider the BCNF a special form of third normal form, and they figure it's just third normal form. They're not going to call it anything else. So the table is in third normal form if it is in second normal form and there's no transitive dependencies. The table is in third normal form but is not in BCNF if there's no transitive dependencies, or maybe some exist, and when one non-prime attribute is dependent on another prime attribute, which means the job code depends on the job description, maybe. And no non-key attribute is determinant of a key attribute. So here we have this. We have the job description, or the job code, with the job title and the hour. So as a kind of an illustration here, the table that is in third normal form but not in BCNF, if A and B determine C and D, job code and job title, like 512 and programmer, determine the cost or something else, where one of them could determine it, or the other one could determine it, or both of them together could determine it. You just pull it out. So you're going to make another table out of it eventually. So here's how it works then. So then you have the third normal form, but not in BCNF. It's all in one table. And then it's in first normal form if you have the partial dependencies in there. It's in third normal form and BCNF if you pull out the other determinants. And here's third normal form of BCNF, where you've got the C and the D. C and the B is over here. So you're going to take that table and divide it into two tables. And then if you divide it into two tables, then you end up with job code with programmer. And then you only have one, 511 and 512. You'd only have one. So 511 is programmer, 512 is database person or something else. And then you have 512 making $10 an hour and 511 making $35 an hour or something. So you change out the hours. So you basically, instead of 3 elements, you'll have 2 and 2. So you add another element to it, the job code that's going to keep them all consistent, and then you just create another table out of it. It's an interesting concept. A lot of people wouldn't do that. They'd leave it all together because it's easier to find the data. So here's some sample data for the BCNF conversion that we're looking at. Student ID, staff ID, class code, and enrollment grade. So student ID 125 was with staff 25 in the class code 21334 and got an A. So looks like the student was in 2 classes, got an A and a C. So we're going to pull this out into 2 separate tables. If we do that, we get this here, where we get another third normal form but not BCNF example, where we have the student number, the staff ID, class code, and the enrollment date. That's this 1, 2, 3, 4 columns. And then we pull out student ID, class code, enrollment grade. And then we have the class code with the staff ID. So we're taking the class code and the staff ID, pulling it out. So we have, instead of 4 columns in one table, we have 2 and 2. It's really 3 and 2, but because we have to link this table with the class code. So we pull out the staff ID because we have a little bit. You can sort the table by the staff ID, or search the table by the staff ID, or you could search it by the class code to see what the grade was. Because if you do it this way, you have 2 different staff IDs teaching 2 different classes. So most likely, probably, you wouldn't be able to tell which staff ID was teaching which class if you just searched on the class code. So basically, it's BCNF because you're pulling it out and making another table out of it. So when in doubt, the higher the normal form, the more tables you have. So you look at it and you go, I mean, it's not necessarily the more tables you have, it's the more logically designed the tables are. If it's all in one table, it's first normal form. You start pulling it out, you're going to get into second, you're going to get into third, and then maybe you'll even get into BCNF. So you can get even further, you can get into fourth normal form or fifth normal form as well by just pulling it out even more. The higher you go up, the more you spread out the data, the harder it is to put it back together. So when you get into fourth normal form data, you have to join too many tables. And people don't want to join the tables because it's expensive from a query perspective. If it's in first normal form, you can't search it. If it's in fourth, you can't search it. I mean, it's just too hard to. It has different problems for why it's hard to search. First normal form, it might be impossible to find the data. Fourth normal form, it's just going to take too long because you got to join this table with this table, this with this table, because it's all spread out all over the place. And then you're adding in more redundancy, more controlled redundancy the higher you go up, because now we have this same piece of data in 2 different tables instead of just in one table. So we may actually be taking up more disk space as well at the same time. So the higher the normal form, the not always the best form, which is why the third normal form is the de facto standard. It's like at the balance point. It's spread out enough so you can find everything, and it gets rid of the data redundancies and then abnormal kind of data inconsistencies. But it's still searchable. It's not broken out that much to the point where it's hard to put it back together. So normalization and database design should be part of the design process. Make sure that the proposed entities meet the required normal form before the table structures are created. Many real-world databases have been improperly designed or burdened with abnormalities or improper modifications during the course of time. Here's the other thing too. So as the database lives through the next 10 years or 15 years, people add more stuff to it, change stuff in it. It's a living kind of piece of software, sort of. It's not really software, but it's an entity. It's an existence of something. If you're constantly changing it or adapting it or moving it, it could lose some of the data that was there in the past, or it could make the data unfindable. That's the idea of whenever like you go to a database table and you see like you have 2 employee tables. It's like, wow, or you have 3 tables because you have duplicate data because somebody didn't realize you have that table, and then they build another table to put something in there, and then they go, oh, wait a minute. So we have some employees in this table, and we have some employees in this table over here, and all of the tables themselves have multiple different pieces of data that represent different characteristics, so you got to go through and search multiple tables. So anyway, that's common problems actually that occur in database designs. The ERD diagram would get rid of the duplicate entries or the duplicate tables. So a lot of people will start out with an entity relationship diagram so that they don't have, or they, for identifying multiple entity occurrences instead of identifying an entity, then they would have, hopefully starting out with a better form where they don't have multiple tables in a case where they only need one table to keep track of an employee or something. So normalization from the ER diagram perspective provides the bigger picture, or the macro view, created through an iterative process, identifying relevant entries and attributes and relationships and so forth. So, believe it or not, that's everything you ever needed to know about entity, how normalization works and how it relates to entity relationship diagramming. But if I showed you this initially when we started looking at entity relationship diagramming, it may not have made any sense to you. But hopefully now that you have that historical kind of experience of creating those diagrams and understanding hopefully how the diagrams work, you can sort of see why that approach is actually easier than taking a bunch of data, throwing it into a table, and then trying to take that data and separate it out. Most likely you'll miss data in that case. Alright, so I'm going to end this video. And then next what we're going to do is assignment number 5 to translate. So we'll go through we're going to go through an exercise that applies first, second, and third normal form translation, which is the start of the next